Good afternoon, everyone. Happy Thursday. Thanks for joining DoubleRadius for our webinar today. Our topic is E-band opportunities, offering premium gigabit service. And we're excited to have our speakers today, Jeff Holdenrid and Caleb Nauer. They tag team over here at DoubleRadius to engineer wireless solutions for all kinds of scenarios. They've been doing this for a long time, and they bring a ton of experience to the table. So you should have some good takeaways from the presentation today. Just a couple things to note before we get started. Please do enter your questions into the questions box so we can try to answer those for you. And at the end of the webinar, please just take a moment to fill out that survey that's going to appear on your screen. So having said that, let's jump right in. I'll turn it over now to Jeff to get us started.
Thank you, Chad. First of all, thank you guys all for being here today to learn about E-band opportunities. Like Chad said, please type in your questions in the question box, and we'll try to jump into those as we go or cover a few of them at the end. If we do not cover your question with an answer today, we will make sure that someone on the DoubleRadius team will get back to you shortly with answers for your questions. So let's kick it off. So why are we here today? We're going to learn about what exactly E-band microwave or millimeter wave is, how fast and how far can these frequencies and these radios really go. Some premium service applications, the comparisons of millimeter wave to microwave and fiber, how millimeter wave complements fiber, benefits and considerations, and then current vendors that out there that have products that fit into this frequency band. So what exactly is E-band microwave? The funny part is, just to get going, E-band actually falls into millimeter wave. And millimeter wave is not a new technology at all. In fact, it's been around for over 100 years. And it refers to electromagnetic waves whose wavelength fall into millimeter range. And that's where this all began. But back in 2003, the FCC launched, They launched the kind of the start of this whole band and these open frequencies that weren't being used. So this spectrum consists of 70, 80, and 90 gigahertz. To be exact, it's 71 to 76, 81 to 86, and 92 to 95 gigahertz. So it's approximately 13 gigahertz of spectrum that's available in this band. Okay. So when you go to, this is a licensed or lightly licensed frequency. So basically what you do is you get a national license for the frequency, and then you load in the data of your link, and you basically purchase the license for that particular link. But you're purchasing nationwide, right? So how are you protected on this link, being that it's lightly licensed? Interference, so this is directly from the FCC's website, right? The interference protection afforded to a link is based on the date and time that the link, new or modified, is submitted to a third-party database manager. So your protection is based on when you actually file this information with a third-party manager. There's companies out there like Micronet, ComSearch, or just a couple that are third-party managers of these frequencies. So how fast can an E-band radio or millimeter wave radio go? And today you have a lot of options out there, but in a 1+0 scenario, we're seeing speeds of 1 gigabit, 2.5 gigabit, 5 gigabit, and then even as much as 10 gigabits. Now, a lot of the systems that are available today can be doubled up or put into a 2+0 scenario, and you'll see marketing specs on some of the manufacturers that actually hint to the use of 20 gigabits in one of these systems. So having the ability to do high bandwidth is really what is attractive on these things. It's something that's been, the demand is driving. The demand for high speeds is driving for 5G and also for these microwave, for these projects that we've seen today out there. And this is where these things are a good complement to fiber. So how far can an E-band radio really go? Because this is a millimeter wave, we're high up, as you go higher in the frequency bands, the distance go, they go shorter and shorter, and we're going to get into that in a few minutes with Caleb. But really, this is where things get really tricky. This is not a frequency that you want to push the limits on. This is a frequency that you really want to make sure that you do your diligence, you do your path calcs, and you double check everything, right? So where in the world will you install this? And I want to give you a couple examples here that we've put together to kind of give you an idea of, what you look at distance-wise of these links, right? So here's an example, and I use two different link calc tools to show this so that we could see, just different ways of looking at it, and also kind of proving the same point with different tools, right? So this is a 1.2 mile link designed in Nevada, right? Not anywhere in specific, but in Nevada. And the system on the left, you can see is approximately, a 10 gig system, at the highest modulation scheme. And you can see the reliability, your 5 nines reliability, at your BPSK. And as things dropped lower and lower, all the way down to 128 QAM, right? And you see your fade margins on this link. Now on the right, you're looking at a 2.5 gig system, roughly the same way, right? Same link, exact same specs of the link, just a different tool, different radio. And you can see at the far right there, which is the highest modulation, we are running a 99.99% reliability, roughly. We're just underneath that on the far right. And then you can see how it gets up above 5 nines reliability at the, 500 megs, maybe 750, give or take a few, right? And this is sitting in the West, where it's a lot drier and, the air is drier and everything else, right? So then let's do the same thing. 1.2 miles in North Carolina, a lot more humidity, a lot more rain. So this is the same 1.2 mile link in North Carolina. So as you can see here, the reliabilities, the system on the left, fade margins, but you look at the reliabilities, now we're starting off at BPSK with a 3 nines and an 8. And in 128 QAM, we're running 2 nines and an 8, right? So the reliability is just not there, is not the same of what we saw in Nevada. This is obviously not as reliable of a link, the same distance, just two different parts of the United States. And we're just using the US as an example here. Now, if you look at the right, we're looking at the 2.5 gig system, same 1.2 mile link as before. And you are seeing that we are 3 nines at just below 2.5 gigs. And we only reach 4 nines at probably about 300 or 400 megs is where we're seeing, you can see that 500 teeter-totters out a little bit, but truly 4 nines, we're below 500 megabits on this link. So if I toggle back and forth, you can see the difference in reliability between these two systems. So Nevada, North Carolina, same distance, just two different parts of the United States. And this is where it's really important to pay attention to what you're doing and how you're deploying these systems. This is not meant to be a system that goes 5, 10, 20 miles. You want to keep this at a shorter distance and keep your reliability moving in the right direction. And here's there's a rain rates. So this is a chart. I know this looks really funky with a lot of colors, but this is basically a chart of the entire world, right? And if you're in the United States, you want to focus on the left side, upper left side, where the United States is. And if you can pinpoint where Florida, Maine, California, Washington, all those places are. So in this case, Florida is considered an N rain rate, right? So in Florida, that is figured out to be 95 millimeters an hour, right? So then if we go over towards, even if we come up to North Carolina where we are, that drops to 63 millimeters an hour. And then if you head over to the west, like Arizona and all that sitting in Eve, you're down to 22 millimeters an hour. And this is really where a lot of this plays into effect on your distances and your reliability. So these are tools that you need to use when you're designing these systems to get your reliability and figure out how well these systems are actually going to work. Now, to go into this a little further, I want to invite Caleb in to talk a little bit about how rain affects millimeter waves.
All right, guys. My name is Caleb Maurer. I want to talk to you guys a little bit about not only how your rain and atmospheric loss is applying to just millimeter wave or the E-band stuff we're talking about, but millimeter wave in general and also some just higher frequencies in general. We found that people that are new to using this type of gear don't understand the bare principles, and it's super important that you understand, what we're talking about here. So these are important concepts. Because it's going to interfere with, or it's going to deal with how you plan your link, your reliability, your planning for failovers that we're going to talk about later, and some other things. So this is the most important part of your link planning. Don't fall in love with spec sheets. These spec sheets from all these manufacturers are definitely showing true information, but you have to realize that once we start dealing with these higher frequencies, that these distances that might be offered aren't necessarily applicable to your area. Oh, this will go 10K, or this will go 20 kilometers, 5 miles, or whatever else. And yes, while that may be technically true on the dark side of the moon, it may not necessarily apply to your given situation. So we're going to talk here about signal attenuation, which is a fancy word for absorption, loss, however you want to consider it, not to get too pedantic here, but we're talking about signal attenuation and how it's affecting your link. Now, there's a lot of math, there's a lot of charts, there's a lot of crazy looking things that you're probably not used to seeing, and that's fine. Luckily, there's some link calculators that are going to handle all that for you, and we'll talk about that here shortly. So this first chart that we look at is not necessarily rain affecting your different frequencies, but this is showing attenuation in dB per kilometer for the whole range of useful bands that we're talking about that is shooting through the atmosphere. Now, this is not a free space path loss calculation where you're just ignoring oxygen and air, just raw loss. What we're talking about here is what happens to these different frequencies as they propagate through the air. Now, generally, the higher your frequency is, the higher the loss that you're going to have through the atmosphere, your higher your attenuation. Now, if you look at this graph here, you're going to see it's kind of linear. Well, as linear as you could be in logarithmic glass, but again, pedantic. The main thing to note is two things. One is generally, as your frequency goes up, your attenuation goes up per kilometer, but there are some interesting spikes. If you see that first little nub spike there on the left between 20 and 30, that's right at 24 gigahertz. Now, you have a higher spike in attenuation on 24 gigahertz because that band is actually being affected by water vapor in the air. Now, we're considering this a global average, and we're looking at this at sea level. All these things really depend on, where you are exactly. But for all intents and purposes, it's a very sort of generic graph about how these bands are affected. So 24 is really affected by your water vapor in the air average. So that's going to cut down your link distance, and that is going to have it more affected by rain fade a lot more than 23 would be or 25 would be. Now, we don't use 25 generally, but 23, a license link, is a very common use. You have less loss on 23 than you do on 24 because of water vapor. You'll notice also there's a big spike in 60 gig. Your 60 gigahertz is commonly referred to as your V band. So E band is your 7080, your V is in Victor band is 60 gig. You'll see a big spike there. And we see a big spike there because that's due to oxygen molecules in the air because of the tiny, tiny size of the wave on that, and then frequency resonances and a whole bunch of nerd stuff. Basically, what happens is right there around 60 gigahertz, that signal is absorbed by oxygen molecules a lot higher than it would be in the 50 gig range, a lot higher than it would be in those 64 gig and above. So that's really going to cut down your distances on what you're going to be able to do with your 60 gig stuff. Your E-band, if you look past that graph right there around 70 or 80, you'll see that atmospheric attenuation concerns kind of level out to the general mean that we see here on this graph, which is good. It's plannable. We like that. And then we can use this to push these links further than what we would typically see on a 60 gig band. So that's just, again, shooting just through air, but I want to talk about rain now. So we'll go to the next slide. And it's kind of hard to see with the amount of lines and stuff in here, but what this is basically a graph that shows you attenuation per frequency, and this is in dB per kilometers, based on various rain rates that you see here. So if you look on the right-hand side of the key at the bottom, you have that 0.25 millimeter per hour drizzle. We have light rain, medium rain, heavy rain, downpour, tropical monsoon, and then 200 millimeters an hour you're not necessarily concerned because all your stuff is washed away. You're done with it. So we'll ignore that for now. Now, one really important thing I'd like to point out here is if you look, for the most part, anything 10 gigahertz or below 10 gigahertz, generally not affected by rain. It is a little bit, but the effects are so small, we typically don't care. So those of you that are primarily been working in 5 gig for your point-to-point unlicensed backhauls, you guys aren't used to dealing with rain fade because the rain affects it so little that it's not coming up in your day-to-day performance. Once you get above 10 gig, though, it does start to affect it. And the higher you go in your frequency, you go from 11 gig, 18, 23 licensed bands, you have 24 unlicensed, you have 60 gig unlicensed, and then this E-band 80 gig light license stuff. The higher that frequency goes, the more these bands are affected by rain. Now, there's a lot of graphs here, and there's a lot of lines. It's really hard to calculate, and we don't really know what this references. These are all tied back to those ITU rain rates. So if we bounce back a couple slides to our mishmash Bob Ross painting here of ITU rain regions across the world, what we're going to see here is, in general, they've come up with these global averages that says for this area, region M, the southeast, where I'm obviously from, the max rain rate that we use for the 0.1% or 1.01, I always forget, is 22 millimeters per hour. So that's a heavy rain, what's considered a heavy rain for here. And it's the calculations and the ITU spits out data that says, given this percentage of time, you're going to see this heavy rain amount. I always like to point out when we talk about rain fade, we're not talking about the amount like global rain, we're talking about the intensity of a rain. So if you get 1 inch of rain over 24 hours, just have a light rain, that might not affect your length. But if you get a really dense rain, you get that 1 inch in an hour, then that's going to affect it heavily. And it kind of comes up with some sort of counterintuitive numbers. You think of somewhere like the Pacific Northwest, you're like, oh, it rains there all the time. Well, it does, but a lot of that rain isn't really heavy. So it'll have less effect. You see that's region D, that in the Pacific Northwest, because that rain is not intense, even though they have a lot more rain over a given day or year average, it's not as intense as it would, so it's not going to affect your link distances. Now, I know this is a ton of numbers to keep up with and graphs and pictures and everything else, so what do? What do is use link calculators to get this figured out. All the manufacturers that are working in this band either give you free calculators that you can use, or they will run this link for you, or a mix match. Hey, here's a simple calculator. You can figure it out and say, sanity check. Can I do a 2-mile link here? You punch in your numbers. Well, no, that's not going to work. But if it's close, you're like, hey, this is feasible. Let me play with some ideas. Then get in touch with us, and we can get you in touch with our engineers if need be, and kind of work out the details and explain, well, yeah, you're going to get this, but maybe not this, maybe tweak 10, whatever you may do. So, again, luckily, these calculators exist. Ciclu's got one on their website. SAF's got one on their website. KMN's got Link Planner. These other guys, your CF, your BridgeWave, some of the others, if I forgot anyone, totally apologize. But they've either got calculators to use or they'll run these calcs for you. Now, one thing I always like to point out with calculations is that you can't always necessarily punch in one manufacturer's radio and expect the calculator from another manufacturer's to give you accurate information. Because all of these units, while they're generally in the same area, there's a lot of differences. One might have a little more output power. Maybe one will support smaller channels, cuts down on your thermal noise. You won't go as fast, but you can push that link further. Some have different receive sensitivities. Some have different values, where their fallback rates are. So, there's a lot of individual sort of tuning for a given link or for a given unit, and you can't always necessarily rely on someone else's data. So again, it's really important that you use a calculator for sure, right? You definitely got to do that to see if your link makes sense when you go to spend a lot of money to use high capacity links. You want to make sure it's reliable. Use the manufacturer's calculators that are available, look at what they're tuning, and look at some of the data things they offer. Maybe we're looking at ITU rates, but unfortunately, seems like global environmental changes over the last while have kind of caused some of these rates to be a little too wishy-washy. We need to make a more conservative approach. So we use, instead of ITU, we use Vagance or some of the crane models or some of these others. Some people have access to path loss. Path loss is a super powerful tool that takes into your heights, your locations, your altitudes, and your directions, and a lot of other information that spits this out. So, you know, getting super preachy, as I have a tendency to do, imagine that. But again, you know, if you're not used to dealing with these high frequency bands, it's not black magic. I mean, it is, but it's okay because there's all these calculators that are available. Definitely use them. If you don't know how, reach out to your sales rep at DoubleRadius. We'll get you hooked up. We'll get it figured out. And with that, back to you, Jeffrey.
Thank you very much, sir. Thank you, Caleb. Appreciate that. So as we move on, all right, now that we've learned a lot about kind of rain rates and how they affect the links, especially in these frequencies, let's talk about, you know, comparisons. You know, how does millimeter wave compare to microwave, right? And when we talk about microwave, mostly, you know, we're discussing, you know, 6 gigahertz, 11 gigahertz, 18, 23. These are all part 101 bands that are obviously lower in the frequency. Millimeter wave, because of the size of the spectrum that we have availability and the channel sizes that can be used, we're able to carry a lot broader bandwidths, you know, with these frequencies, right? Usually when you think of a microwave system, you think of 100 megs, 500 megs, 1 gig, stacking multiples to do multiple gigs, right? When we talk about the millimeter wave, obviously when we brought up earlier, we talked about 500 megs, 1 gig, 2.5 gig, 5 gig, 10 gig. So we're carrying a lot, you know, broader bandwidths with millimeter wave. There's obviously, because these wavelengths are so small, there's a lower probability of interception and interference. And then the antenna sizes on millimeter wave are primarily a lot smaller. You know, when you think of a 6 gig link, you're usually carrying that 10 miles, which we're not doing here, or, you know, 20 miles. You're using 6-foot dishes, 4-foot dishes, 3-foot dishes. Most of the time in the millimeter wave, they are using an integrated antenna, a 1-foot dish, and or a 2-foot dish. So your antenna sizes are a lot smaller when looking at the millimeter wave systems, okay? So let's carry on, right? Millimeter wave and fiber, right? These are little bandwidth comparisons, okay? So fiber obviously is, you know, we're talking about glass and light and everything else, and it carries, no matter how far you run you know, you run the fiber, you know, 5 miles, 10 miles, you still have the same bandwidth carrying through it. With the millimeter wave, as we get further distances, we are slowing down in speed, and that is a difference between the two. So we're not carrying, you know, if we say it's 10 gigs, obviously we're using our path calculators to keep it to where it is reliable within that speed. But as we carry max distances, that will drop off as we go farther and farther with the millimeter. So that's kind of how the bandwidth comparisons go between the two. What about cost comparison, right? We know that, you know, when it comes to fiber, you know, every mile is additional cost, right? Every half mile is additional cost. Every block is additional cost. When it comes to millimeter wave, we're talking about per end cost, right? So when we have building to building, across the street, down a mile, however far we're trying to carry this link that's within spec, it is the same cost. So it does not increase cost as you go farther and farther. It is the same cost. Now, once again, we still run into those distance limitations, but you understand where there is that fine middle point where the millimeter wave will save you money. Now, if you also add to that, how long does it take for you to get a permit to run fiber? How long does it take for you to actually bore and put the fiber in place or hang the aerial fiber, right? Where a millimeter wave, you could buy it today, you could have your license done, and you could deploy it, you know, roughly within no time at all. You're starting to gain return on investment right away. So that's one of the cost comparisons you also need to take into effect when you're talking about millimeter wave and fiber. So how do they complement each other? And we're going to go right into what I just said, return on investment, right? I'm going backwards on this one, but return on investment now. We have a lot of fiber companies today that call us and they're like, you know, we just need to go across the street, or we need to go, you know, we need to cross a highway, we need to cross a body of water, and, you know, or we need to put in something new. And now we put in the microwave and we start getting money now. If it takes 6 months to put the fiber in, that's 6 months of revenue that you can gain by using millimeter wave to complement the fiber, right? So not only is it going to complement the fiber by making crossing highways, railroads, bodies of water easier, you could take a simple solution of shooting from building A to building B and actually start getting a return on investment day one. Those are really the biggest complements, right? Or even extending out. We have a lot of customers today that will have a NOC. They'll have a fiber NOC, and now they'll use mmWave to connect multiple businesses within, a mile or so, and they will end up bringing 100, 200, 1 gig connections to them right out of the gate, and run a hub and spoke, complementing each other using fiber to feed the NOC, and then using the mmWave to be the spokes. And there's a great advantage to that. We're seeing more and more of that every day. It's literally probably one of the biggest growing things we see in the fiber world today is using mmWave to do that. Urban environments, brownfield buildings, places where there's a lot of, where it's tough to wire. We see, in your industrial areas and things like that, mmWave is popping up big time, even in situations there. Okay. So here's a traditional. Let's give an example of something. This is we've worked with some fiber providers, and this is a slide that we got from them. So traditional wireless deployments, you have a tower somewhere near an area, and this is like taking a neighborhood, for instance, right? So you have a tower near a neighborhood. You're using traditional 5 gig, 2.4, 3 gig, and you're feeding point to multi-point. Obviously, depending on where you are in the U.S., like in the East Coast where we are, there's trees everywhere, and you might pull up 5, 6, 10, 10% of the neighborhood. Let's just say that for an example, using traditional wireless deployments. Today, we're actually seeing situations where you will bring fiber into a few key locations inside the neighborhood, right? So you're feeding fiber to few places, using mmWave to connect those places to other key locations in the neighborhood, and then using your traditional 5 gig, 2.4, 365, even 60 gigahertz, and you're using that to kind of feed all your down the streets and actually get more of like a 90% coverage area, right? So this is kind of a backwards way of doing it, but we're seeing this out of a lot of fiber providers on the East Coast where trees are an issue. So they're bringing the bandwidth closer to the homes and then using traditional microwave point to point, point to multi-point to spread it out from there. And they're doing this by supplying, when they do these scenarios here, they have such high bandwidth, they can supply 50, 70, 100 meg connections without a problem because they're bringing the bandwidth so close to the end user. So that is definitely a win-win on that one. Extending the range. This is an example of tying 80 gigahertz with 18 and 23. Some of the manufacturers allow you to couple them together, and you're using a Part 101 license, you're using Part 101 with 18 and 23 gigahertz, and you're using 80 gigahertz to carry your high bandwidth. So what happens in this scenario here is if you run into those rain rates, or you run into those heavy rains that Caleb was talking about, and your link starts to fade on the 80 gigahertz, it kicks over and stays up and running on the 18 and 23, because we know we can carry distances, we're lower in the frequency, so then we're able to carry farther distances. This also gives us the ability to increase speeds beyond what we're currently doing. So if you have, like, for instance, an 18 gig system today running, 500 megs or a gig, now you just put in a different antenna and you can tie the two together, and now you've just add 1 gig, 2.5 gig, 5 gig, a 10 gig, and now you're increasing your bandwidth in that area. And in the picture on the right, you can see how the two are coupled together. Some of these manufacturers will allow that system to run through each other. So it's still, you would wire up the 80 gig and you would have a fiber connection from the 80 gig to the other radio, or the piggyback, or whatever you want to call it. And then you're not running multiple cables. Now, obviously, if the 80 gig fails in that scenario, it doesn't help you. But with your everyday deployments, it's a great way to build added throughput and also have redundancy built in at the same time. So currently today, DoubleRadius is working with Cambium Networks, Ciclu, Bridgewave, SAF, and SIA. All of these manufacturers have their own 80 gigahertz products. They have their own link tools. Every one of them will run path calcs for you, and we also have the tools to run those path calcs with them. We can't stress enough. I mean, when you're doing these mmWave deployments, we cannot stress enough the requirement of line of sight. So double check your work, triple check your work. If you get a manufacturer to do your path calcs, have your vendor check it too. If you get your vendor to do it, have the manufacturer check it too. Make sure that when you do this, you're doing, you're crossing your T's and dotting your I's, and making sure that everything it looks as good as you want it to look. These technologies are changing every day. We're seeing the ability to carry higher frequencies, bigger frequencies. So the speeds are going to continue to grow. But if you have areas where you need short shots and high bandwidth, mmWave is definitely the answer for you to look at. It is definitely a way for you to put the bandwidth in at a set cost. And once again, if you're going to license these radios or these systems, you can work with companies like ComSearch and Micronet. You get your nationwide license. You enter in your link data. You run the interference analysis. You register the links, and away you go. It's very simple, and we can definitely help you with that also. So I know this is a quick, short, sweet presentation with a lot of information. Are there any questions at this time that you would like answered on some of these technologies, on the rain fades, on the capabilities, the latencies, anything whatsoever? If there's any questions, please put them into the question thing, or the ones that we already have, we'll get back to you on for sure. Okay, so then we are going to say goodbye, and thank you again for joining us on this webinar today. We hope you have a great Thursday and have a wonderful weekend, and look forward to talking to you more about about these systems and other systems that we can supply you. Thank you very much.